Look at your hand. Feel its weight, its texture, the warmth of the blood flowing through it. It feels solid, undeniably real, doesn't it? Now look at the space between you and this screen. It seems empty, a passive, silent void, and you can feel time itself, an invisible and unstoppable river, carrying you relentlessly from a fixed past toward an unknown future. This is the reality we are born into. It's intuitive, it's familiar, and for most of human history, it was the unquestioned truth of our existence. For centuries, our understanding of this grand cosmic stage was defined by the genius of Isaac Newton, who saw the universe as a giant, absolute clockwork mechanism. But a century ago, our perception of reality was shattered and rebuilt by one man, Albert Einstein. He gave us a universe woven from a magnificent four-dimensional fabric called Spacetime. His theory of general relativity described a cosmos that was smooth, continuous, and breathtakingly elegant. Imagine spacetime as a perfect, infinite silk sheet. Planets, stars, and entire galaxies are like weights placed upon it, creating gentle curves and dips. What we call gravity is nothing more than the feeling of following these curves. This picture has been astoundingly successful, a pillar of modern science that predicts everything from the bending of starlight around the sun to the precise timing of our GPS satellites. It's the grand, beautiful architecture of the very, very large. But what if I told you that this elegant picture, as beautiful and powerful as it is a profound deception? What if I told you that everything you see, everything you touch, everything you are, might be nothing more than an elaborate projection, a three-dimensional illusion, generated from a fundamental code written on a distant, two-dimensional boundary at the very edge of the universe? Tonight, we are not retracing Einstein's path. We are embarking on a journey that goes beyond him to uncover the most profound, bizarre, and thrilling secret of modern physics. A theory that suggests our universe is not what it seems. Welcome to Universe Scale. The cracks in Einstein's beautiful reality began to appear when we turned our gaze in the opposite direction, not to the stars, but deep into the heart of the atom. There, in the subatomic realm, we found a world governed by a completely different, almost magical set of rules. The rules of quantum mechanics. If relativity's universe is a smooth silk sheet, the quantum world is a vibrant, pixelated digital screen. It's not smooth. It's jittery, chaotic, and fundamentally uncertain. It is a world where particles can exist in multiple places at once, like a ghost that is everywhere until the moment you look at it, forcing it to choose. It's a world built on probabilities, not certainties, where the very act of observation changes the outcome. This is the world that gives us computers, lasers, and the power of the sun. These two theories, relativity and quantum mechanics, are the twin pillars of modern physics. Each is a monumental achievement of human intellect, verified by countless experiments to an incredible degree of accuracy. But they are built on contradictory foundations. One is the language of the smooth and continuous. The other is the language of the discrete and jittery. For most situations, this isn't a problem. Physicists simply use the right theory for the right job, like a mechanic using different tools for the engine and the electronics. But in the most extreme environments in the cosmos, these two great theories are forced into a head-on collision. Inside the infinitely dense heart of a black hole, or within the fiery crucible of the first moments of the Big Bang. Both gravity and quantum effects are immensely powerful. And when you try to apply both theories at once, the mathematics breaks down. It doesn't just fail, it screams infinity, signaling a catastrophic failure in our understanding of the universe. This is the greatest crisis in physics. For a century, the Holy Grail has been to find a single, unified theory, a theory of quantum gravity. In that search, physicists stumbled upon a paradox so deep, it threatened to undo everything we thought we knew. A paradox born from the darkest, most enigmatic objects in the universe: black holes. Black holes are the ultimate prisons of spacetime, formed from the collapse of colossal stars. They are cosmic whirlpools with a gravitational pull so ferocious that once you cross their boundary, the event horizon, there is no escape. Not even for light itself. It is the point of no return. For decades, the story seemed simple and terrifying. Whatever falls into a black hole is stretched into spaghetti, crushed into the infinitely dense central singularity, and is lost to the universe forever. Its story is over. Its chapter in the cosmic book is ripped out. But this simple picture hides a universe-shattering problem. Let's imagine you toss a library into a black hole. Within that library is an immense trove of information. The complete works of Shakespeare, the laws of physics, the history of human civilization, the unique memories stored in a personal diary. According to Einstein's relativity, all of that intricate, meaningful information is simply and utterly annihilated. It vanishes without a trace. But the other pillar of physics, quantum mechanics, stands up and screams, impossible. A core, sacred principle of the quantum world is that information can never, ever be truly destroyed. It is conserved. Think of it this way. You can burn a book, but the story isn't truly gone. In principle, if you had a supercomputer powerful enough to track every single atom of ash, every photon of light, and every wisp of smoke released, you could reconstruct the original book. It's not just the letters, but the story, the soul of the book, that is preserved. The universe, according to quantum mechanics, never forgets. But black holes appeared to be cosmic amnesiacs. They were shredding the book of reality and then burning the shreds. This was the black hole information paradox. It was a declaration of war between our two best theories of the universe. If the black hole truly destroyed information, then quantum mechanics, the theory that underpins our entire digital world, had to be wrong at its very core. But if information was somehow preserved, then Einstein's description of black holes, and perhaps gravity itself, had to be incomplete. This crisis stumped the greatest minds, including the late, great Stephen Hawking. In fact, it was Hawking's own groundbreaking work on Hawking radiation, the discovery that black holes aren't entirely black, but slowly evaporate over trillions of years by emitting a faint glow of particles, that made the paradox so severe. His calculations suggested this radiation was random and contained none of the information that fell in. The information was truly being erased. It was a battle for the soul of physics. The solution didn't come from a grand new particle accelerator or a powerful telescope. It came from a piece of chalk on a blackboard, from a thought experiment of pure genius. Physicists like Gerard 't Hooft and Leonard Susskind began to ask a radical question. What if the information never actually makes it inside the black hole to be destroyed? What if, as an object crosses the event horizon, all of its information is somehow captured and imprinted onto the surface itself? Imagine the event horizon as a cosmic computer screen. As a 3D object falls in, its entire informational blueprint, every atom, every quark, every bit of its story, is encoded onto the 2D surface of the horizon. Each tiny piece of this information occupies the smallest possible pixel size allowed by physics, an area known as the Planck area. Astonishingly, the math showed that the total information of any 3D object fits perfectly onto the 2D surface area of the black hole it creates. The paradox was solved. The information isn't lost. It's stored, scrambled on a two-dimensional surface. But this solution, born from the abyss of a black hole, was about to swallow our entire perception of reality. Because if this bizarre rule is true for a black hole, why not for the universe itself? This staggering idea that all the information required to describe a three-dimensional volume of space can be fully contained on its two-dimensional boundary is the essence of a hologram. When you look at a hologram, perhaps on a credit card or a driver's license, you see a floating, three-dimensional image. It has depth, perspective, and appears solid. But all the information required to create that rich 3D image is encoded in a flat, 2D pattern of intersecting laser light on the film's surface. The pattern itself doesn't look like the image. It looks like a meaningless swirl of lines, but it contains all the necessary data. The light acts as a processor, reading the 2D instructions and projecting the 3D object. The holographic principle takes this concept to its mind-bending, cosmic conclusion. It suggests that our entire, vast, three-dimensional universe could be a holographic projection. Picture our observable universe as existing inside a gigantic, imaginary sphere. The holographic principle proposes that everything happening inside this 3D sphere, you, me, this planet, the Andromeda galaxy, the cosmic web of filaments stretching for billions of light years, is merely a projection. A 3D image whose source code is written in a language of physics that exists on the 2D boundary of that sphere, at the farthest reaches of the cosmos. According to this view, the 3D reality we take for granted is not fundamental. It is an emergent phenomenon. It grows out of a flatter, simpler, more fundamental 2D reality, just as the 3D image of a dove emerges from the flat surface of a holographic film. It means that the feeling of depth, the three dimensions of space that feel so real, might be a grand illusion constructed by the laws of physics from a lower dimensional set of rules. This idea is a profound revolution in thought. It means that space itself, the very stage of our existence, might be an emergent property. It's not a pre-existing container, as Newton thought, or even a dynamic fabric, as Einstein thought. It is the product of something deeper. This led physicists to a startling realization. The amount of information, or entropy, that a black hole could contain was proportional to its two-dimensional surface area, not its three-dimensional volume. This was the key mathematical clue. It was as if nature was screaming at us that reality is fundamentally two-dimensional. So where does that leave Einstein's beautiful fabric of space-time? In this new picture, space-time is no longer the fundamental stage on which the play of the universe unfolds. Space-time is the play. It is the projection itself. It is not the bedrock of reality, but a property that emerges from a deeper informational layer, a layer that may not contain what we think of as space or time at all. This turns our entire worldview on its head. It suggests that at its most fundamental level, the universe might not be made of matter and energy existing in space and time. It might be made of pure information. If our universe is a hologram, it must have a finite resolution. Your computer screen isn't infinitely smooth. It's made of millions of tiny pixels. If you look closely enough, you can see them. Similarly, the holographic principle implies that the fabric of space-time itself cannot be infinitely smooth. If we had a microscope powerful enough to zoom in to the smallest possible scale, the Planck length, the picture of a smooth, continuous reality would shatter. How small is the Planck length? It is a scale so infinitesimally tiny that it's difficult for the human mind to comprehend. Imagine scaling up a single atom to be as large as the entire observable universe. On that colossal scale, the Planck length would be about the height of a single tree. It is the ultimate indivisible pixel of reality. At this scale, theories like loop quantum gravity suggest that space-time dissolves into a network of discrete, indivisible units. Atoms of space-time. From a distance, from our macroscopic view, this quantum network of interconnected loops appears as the smooth, continuous fabric of Einstein's relativity. But up close, reality is pixelated. These fundamental pixels are not in space. They are space. They are the bits, the zeros and ones of cosmic information from which space itself is built. This idea of emergent space-time can be understood with another analogy. Think of the wetness of water. A single H2O molecule isn't wet. Wetness is not a property of one molecule. It's a collective property that emerges from the complex interactions of trillions upon trillions of molecules together. In the same way, a single atom of space-time doesn't have a location or a duration. The properties we call space and time are the collective phenomena, the wetness, emerging from a vast sea of quantum information. The implications are staggering. The laws of physics might not be descriptions of how things move through a pre-existing space and time. They might be the algorithms, the software that processes this fundamental information. The universe at its core might be a quantum computer. And what we call gravity, the force that holds galaxies together, might not be a fundamental force at all, but an emergent thermodynamic property, like the pressure of a gas arising from the random motions of countless atoms. So, are we living in a simulation? The holographic principle doesn't say that reality is fake, or that it was created by some intelligence. But it does suggest that our universe can be described in a way that is mathematically equivalent to a computer system. The ultimate question of physics, what is the universe made of, could be fundamentally the wrong question. The right question might be, what is the universe computing? This isn't just philosophy. The math behind this idea is surprisingly robust. The most powerful piece of evidence is a discovery called the ADS-CFT correspondence, a mathematical dictionary that allows physicists to translate between two seemingly different universes. One is a complex universe with gravity like ours, and the other is a simpler quantum universe without gravity that exists on the first one's boundary. The fact that a perfect dictionary exists between them is a stunning sign that gravity and space-time with it is the hologram, not the fundamental reality. So let us ask, for one last time, what actually are space and time? The most honest answer from the frontiers of physics today is, we don't know for sure, but we know with near certainty that they are not the simple, absolute, and fundamental concepts our ancestors believed in. They are something much stranger and far more magnificent. Our journey of understanding has been an epic odyssey of human thought. We began with Newton's clockwork universe, a predictable and eternal stage of absolute space and time. Then, Einstein, a lone genius, shattered that stage, revealing a dynamic, flexible fabric of space-time that could bend, warp, and ripple. For a century, we have explored this new reality. And now, the search to unite Einstein's world with the bizarre quantum realm has led us to the most radical idea of all, that even that cosmic fabric might be an illusion. A beautiful, intricate, and convincing illusion. Perhaps space and time are not fundamental components of reality at all. Perhaps they are an emergent user interface, a beautiful and effective operating system that evolution has crafted for our consciousness. An interface that allows us to navigate a reality made not of substance, but of pure information. A reality whose true nature is far beyond our limited sensory experience, written in a mathematical language we are only just beginning to decipher. The quest for a theory of everything has transformed. It's no longer just a search to unite the forces of nature. It has become a quest to find the source code of reality, to read the algorithm that projects our cosmos and ourselves into existence. The journey that Einstein began has led us to a cliff's edge, where we now stare into a reality far stranger, more intricate, and more beautiful than he could have ever imagined. The great book of the universe is still being written, and the next chapter promises to redefine what it means to exist. So the next time you look at your hand, feeling its solid reality, or gaze up at the vastness of the night sky, remember what you've learned tonight. You might not be looking at a world of things in space. You might be looking at the most complex, beautiful hologram imaginable, and the quest to understand it continues. With us. What do you think? What is the true nature of our reality? Share your ideas in the comments below. Thank you for joining Universe Scale on this mind-bending journey.